Hi everyone, welcome to another JSO tutorial. In this tutorial, we're going to continue creating a nonlinear optimization solver using the JuliaSmoothOptimizers packages. Okay, so first let's take a quick look at what we have done. We installed a few packages, so NLP models and solver tools to define a JSO compliant solver. And we tested our solver against IPOPT using NLP models IPOPT. Then we use solver benchmark to create a table. We're going to explore a little bit more this option, and then we're going to create performance profiles. So we are creating a SQP solver, which is essentially just applying the Newton method for systems to the KKT conditions, and we are not making any kind of control of the steps. We are using the full step. So here we have the solution, and we use the full step. Okay, of course this method is not gonna be very good, but we are happy just using it. Next, we show the output, run a few manually inputted problems, and then we created tables of these problems. This was just run, okay? So here I'm using IPOPT. I run IPOPT in the same problem, and I can compare both of these problems, the solvers. Here I'm comparing SQP and IPOPT. Okay. Okay. Now it's time for the second, or actually, now it's time for the third tutorial on JSO, which is gonna be comparing our solver and IPOPT on CUTEst problems. So the first thing is that we're gonna install CUTEst. This has to download a few things, so it may take a while. So here I installed CUTEst. I'm gonna use CUTEst. And notice I'm installing CUTEst just now. I'm not using a pre-installed version. And in this CUTEst, I'm gonna use a function called fetch. Autocomplete, please. Fetch CIF problems, which is gonna download all problems, unless my I can't run that from the notebook. So I'm gonna go to the terminal, run that. So here I'm in the same situation as here, CUTEst 010. I'm gonna use CUTEst. And then CUTEst.fetch CIF problems. So that's it. I think I already had them downloaded. We can test this creating a model. I think AJS7 is a good example. And then we can run. I have to use NLP models. So yeah, that's working. Let me explain the details back in the notebook. So here I'm gonna run this, run in your terminal, and well, let me check if I can just run this. Yep, it works. So what's happening here? CUTEst is a collection of problems. It was initially created, I think, in the 80s with the name Qt, then Qter, and now CUTEst. And it's a collection of problems written in Fortran, which provides the function and derivatives in a very efficient manner. So it's been used in research for like 40 years, something like that. if you're gonna work on comparing your solver to another solver from nonlinear optimization, you're gonna want to use CUTEst problems unless you're working on very specific problems. Okay, so if you're working with quadratic problems, then of course you're gonna look into specific repositories. But CUTEst is the most general one with the larger amount of problems. So it's well known and widely used. So here I have CUTEst installed and using, and now I just run NLP equals CUTEst model. So why am I using CUTEst now since I was using NLP models? What changed? Nothing. Because CUTEst model is an NLP model. Okay? So what I'm saying is that CUTEst or CUTEst.jl implements the API of the NLP models.jl. That means that this problem can be run on our solver. We just have to make sure that it's an equality constraint problem and it doesn't have bounds. Okay, not has bounds, not auto-completing. Okay, so it is an equality constraint problem and doesn't have bounds. We're gonna run on our SQP NLP. So there you have it. I ran problem HS7 using our SQP method. So this is the log of iterations, and it found the solution minus 1.7. Okay, so where did HS7 came from? Because I work with CUTEst, I know that HS7 is the name of a problem inside CUTEst. Is the problem from the Hochschild-Kautsky collection, the 7th of the problems. But if you're not accustomed to all these problems, what you can do is select the ones you want. So what we're gonna do now is select problems under a specific criteria. We're gonna select problems with up to 2 variables, at least 1 constraint, up to 2 constraints. And since our solver does not handle inequalities and bounds, we're gonna say that only 3 variables and only equality constraints. Okay, so you can use the help to check these options. pnames equals that. Sorry, this is CUTEst. pnames equals that. There are 28 problems which satisfy this criteria. So what we're gonna do is run our solver SQP on these problems. The first thing here is that for our solver benchmark, you need to pass a list of problems. So you need to pass a list of problems to benchmark solvers or solve problems. Okay, solver problems, no, solve problems. So you need to pass a list of problems, and pnames is a list of names. And the issue with CUTEst, or not specifically with CUTEst, but with using Fortran libraries that you have to open, is that the way it works is that it compiles a problem and then it provides to you the problem to that object. So I have a specific function for AJ7 that was enabled when I said CUTEst model AJ7. So if I do CUTEst model AJ8, is gonna conflict with that one from AJ7. So what I have to do is finalize our problem. So let me just show you. If I say CUTEst model AJ8, it's gonna say call finalize on current model first. So you can't open more than one problem at the same time. Okay, so this is a known issue. We'll very much like to fix this, but no solution in sight. So what we're gonna do, what you have to do is finalize this problem. Okay, so here it is finalized. Now what we're gonna do is create the list of problems. But since these problems have to be open one at a time, I can't create an actual list. I'm gonna create a generator. So I use this parenthesis, CUTEst model, P for P in P names. Okay, so this is a list of problem names. And for each one of those, I'm gonna create a CUTEst model. Except that it is inside parentheses, so this means a generator. Okay, so just a quick generator versus vector comprehension. How do you write comprehension? Let's leave it this way. If you say I for I equals 1, 2, 3, you're gonna have 1, 2, 3. And if you say I for I equals 1, 2, 3 in parentheses, you're gonna have a generator object. Okay, so this one is gonna allocate this vector, and this one is not gonna allocate the vector. So for 10,000 elements, you're gonna start to see the difference. So back, we have our problems. Here is a generator of CUTEst models. So it's gonna call CUTEst models on these guys. And what we're gonna do is say solve problems, our solver SQP on these problems. So this is our data frame. And this is the output. This doesn't look as good as if it were on the terminal, but you can see most of the information here. So I have at each line the problem name, number of variables, number of constraints, what happened, so the exit flag or status, the time, and I think I have the function value, dual and primal measures. So here the function value, dual and primal measures. Okay, so our solver solved this, and this, and this, and this. It has a maximum evaluation exit flag for problem power SQ. It had an exception, so this is important. We have an exception in our solver for problem HS9. Notice that it did not explode and failed. It simply said, okay, you had an error, so the exit flag is exception. And we can see from the log, because we have exported the exception, that the problem was a singular exception. So our matrix was probably singular or close to being singular. So more problems being solved, another singular exception, maximum number of evaluations for Hemel BD, another exception, maximum number of evaluations, another exception, and that's it. So this is it, well formatted. Okay. Say you want to look at the kind of histogram of problems, you can do something like dictionary for you're gonna write this for K in unique df status, and what you want to check is the sum. I can say count. Yeah, I'm gonna say count of df status equals K. So there you have it. When we ran our problems, we found 21. There are 28 problems under our criteria, so 21 of those are first order, 3 have found the maximum number of evaluations, and 4 were exceptions. Okay, if you want to know which ones are exception, you can use again this to select the indexes and then the f of that. You actually have to write this. So these are the problems, okay? HS9, these are the one, FLT, and cluster. For now, we have this run of our SQP on these 28 problems. We're gonna accept that our solver is not good enough. We're just gonna compare it against IPOPT. So we already have a solvers here, and we're gonna use stats equals bmark solvers and problems. So this is running everything from SQP and IPOPT. It has stopped. And what we're gonna do now is create a performance profile. So I'm gonna add a new package, which is actually the package is already implicitly added by solver benchmark, but I think I'm gonna try to use it directly. So solver benchmark dot performance profile. So performance profile of these stats, and I have to pass here the stats and the cost function. So the stats is just the stats that we have used, which is a dictionary of data frames, and the cost is the cost function. How do I evaluate a solver? So here we're gonna use a cost function that is simply the elapsed time. Okay. I think I thought I needed the cost names. A performance profile is a kind of evaluation between solvers. It evaluates how fast the solvers solve the problem in comparison to other solvers. So it's also a well-known tool, and I think 2002 it was released, the paper talking about it. So here it is. This is the performance profile of our 28 problems, IPOPT and SQP. So at the left, I have the efficiency of a solver, so how fast it is. And at the right, I have the robustness of a solver, how many problems it has solved. Okay. So here you can see the log scale that this is very small. So IPOPT has a little bit of an overhead, and then it how to say surpass, and then it surpasses SQP very fast, and SQP starts fast solving problems because it essentially just does a system and doesn't make any special calculus, but it doesn't get any better than about 80%. Okay, sorry, it doesn't do any better than 80%. IPOPT, on the other hand, it takes a little bit to start, but very quickly it surpasses SQP, our SQP. Okay, so this is expected, of course, since our method was implemented in less than 2 hours. What I'm going to do is move ahead to creating a LaTeX table from this. So I'm not sure. Yeah, I have created a LaTeX table in the past. So I'm just going to create a LaTeX table here. The columns that are interesting for me are, so open SQP results.tech, do IO, stats, and columns. The name, the status, objective, the elapsed time. So I could create as well, and here I actually want SQP. I could create as well, let's do this one first and then I show the other one. Forgot to say write. So opening with writing permission. Let's see what happened. So I have SQP results here. And I'm gonna create a main tag. It's gonna be a standalone. Actually, I can create an article here. Use package UTF-8 input enc and package long table. And you can include the SQP results.tech. I'm gonna use a LaTeX make to make my PDF. So I had a failure to make, yeah, it's using SQP tech. So this is my table. Okay, beautifully formatted. So this is the results. These are the results of my SQP solver and the 28 problems. Okay, this is essentially ready for publication. It's well formatted. You see the elapsed time here. If you're not happy, you can change a little small details. Here, since I also want the number of function evaluations, I can create a new sum counters, which is gonna be the sum of the other counters. So I just have to remember how I do. Yep, and comma. No, this first one, and then I have a comma and a vowel obj. Yeah. Yep. So this is an vowel obj counter. What I'm gonna do is sum all of this. So I'm gonna sum C for C in names, field names actually, of my counters. So I'm summing all of the counters here, but if you want just the number of function evaluations, you already have that. If you want the function evaluations plus the constraints evaluation, you can select that as well. So this is a self-service. So I need to recompile. Reopening. So here it is. So this is the amount of function evaluations that I needed to arrive at this solution. Okay. So you can see that in max eval for power SQ, I made 104 function evaluations. So the maximum was 100. So in the middle of the iterations, it makes like 4 or 5 evaluations. So that's why. Same thing for HemoBD and Furlron. Okay. So what I can do as well is, since I have made a performance profile using the elapsed time, I could make one using another cost function. So let me just check that if I already have these cost functions. So here's a cool example as well. In the case I don't have a first order, I can say infinity. So it takes in consideration when I do not solve the problem. That's important. Let's use this one. A quick trick here. If I have the status different from first order, the cost is gonna be infinite. Infinite. Gonna be infinity. Okay. So this is penalizing when I do not solve the problem. Okay, which apparently happens a lot of times. I know it happens 7 times for a solver. And here for IPOPT, it found infeasible, 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 feasible a couple of times for IPOPT as well. So this is more like the actual solution. A different one would be using the sum counters that we have defined. So I have defined it for SQP here. I'm gonna define it for IPOPT as well. And here, instead of saying df elapsed time, I can say df sum counters. I forgot an and here. So this is the number of functional evaluations it took to solve our problems. So SQP has needs a little bit less functional evaluations, especially because it does not make any kind of search, so it's much simpler. IPOPT needs a little bit more to surpass SQP. Okay, so this is the basics. Our next step now would be to create a better solver. So what we want to do is use sparsity to solve this problem a little bit better, or create a solver with a matrix-free or factorization-free approach. So our solver currently solves this, is in the beginning, solves this system, okay? And what we want to do is create this matrix using only the sparse arguments. And I mean passing the row, columns, and values. The rows, columns, and values of each a non-zero element here. Okay, this will be a little bit more efficient regarding our memory. So I'm going to do that next time. Please subscribe to the channel so you can be notified when I get a new video online, and follow me on Twitch and Twitter as well. Okay, I hope you guys enjoyed, and I'll see you guys next time.